Well, ladies and gentlemen, thank you for coming to the lecture tonight. It's a great pleasure to talk to you on one of my favourite topics, the contribution of Einstein to the foundation of a new field of technology, namely quantum technology, and the preeminent example of which is the quantum computer, which I hope will be widespread in the mid-21st century. I'm here today in the United Kingdom. The Australian borders were closed for 2 years, and I managed to, as soon as they came down, I was able to take up a fellowship that had been offered by the Royal Society a couple of years ago, a Wolfson Visiting Fellow, which has supported my visit and my activities here in the UK over the last few weeks. But tonight's lecture, Einstein's Revolution. This is a field of research that I've been engaged with at a practical level for the last couple of decades. And my aim tonight is not actually to present you with the blueprint of a 21st century quantum computer, but to go through some of the physics that sits behind it. And I should acknowledge that the University of Melbourne, where I come from, where I work, is on the land of the Kulin Nation, the first discoverers and colonisers of the continent of Australia more than 60,000 years ago. So this is indeed the University of Melbourne. It's on a pleasant green campus on the edge of the city of Melbourne. You can see the blue waters of Port Phillip Bay in the distance, and the physics building is there in the corner. And what's very important about the physics building is not that it's surrounded by numerous coffee shops where you can go to discuss physics anytime you like, except when I'm giving lectures, but also in the basement is my laboratory. I have a large particle accelerator and a series of beamlines that we use for doing material science, and in particular the material science directed towards our quantum technology projects. We also have a cryogenic system for measuring the properties of materials at very low temperatures, particularly the behaviour of spins, which I'll come on to later on. And over here, just down the hall from the big accelerator, is a small accelerator, which we use for inserting single atoms, one at a time, into crystals of silicon. More on that later. So here's the outline of my lecture tonight. First of all, I want to do a quick retrospective of the dawn of the computer age and what I call the first quantum revolution. Then I want to introduce you to the promise of quantum technology and the quantum atom's useful spin. And finally, I'll wrap up with a quick review of some of the work we're doing on building a large-scale device based on atom spins in silicon. So first, a quick retrospective, the first quantum revolution and the dawn of the computer age. So just recently I made a major milestone, and I had occasion to reflect back over more than 6 decades on planet Earth. So I just wanted to share with you some of those reflections that brought me to where I am today. So in 1958, okay, I've given the game away, the Americans launched their first satellite into orbit. It was loaded with Geiger counters, and it discovered the Van Allen radiation belts. In the magnetic field of the Earth, charged particles, particularly protons and electrons, are trapped in the curving magnetic fields, and they orbit backwards and forwards under the influence of magnetic forces. These radiation belts can be hazardous to humans in orbit around the Earth, and also to electronics, as we'll see later on. But if we fast forward to 1969, wow, what a year that was with the Apollo missions, and standing on the front porch of my home in Melbourne, looking up at the moon and knowing there were a couple of people walking around on that moon was an extraordinary experience, and I followed the space program very avidly. Now, it was sometimes said that this was the dawn of the space age, but actually it wasn't the dawn of the space age, it was the dawn of the computer age. Because for the first time, humans had built machines which were too complicated for a human being to control. And so the lunar module and the command module and the Saturn V rocket were all controlled by some advanced, for the day, computer technology. And indeed, the computer on the lunar lander here had a massive 2,800 silicon chips. Each chip was crammed with 6 transistors, and there was a whopping 70 kilobytes of core memory. And this was responsible for getting the astronauts down safely onto the moon and safely back into orbit afterwards. And if we fast forward to today, there are now robotic explorers on the planet Mars. This is the Curiosity rover. But the Martian atmosphere is very thin, and radiation from space is able to reach the surface. And that radiation consists of energetic ions, protons, the nucleus of a hydrogen atom, which is able to make it down through the thin atmosphere and pass through the electronics on the rover. And this inset here shows upsets in the memory of the computer every time a proton goes zapping through it and maybe changes a bit from a 0 to a 1 or a 1 to a 0, or causes other upsets. And the hardware and the software has to guard against those random perturbations from outside so that the computer continues to operate normally. Now, 1958 was also a big year for Australia because for the first time jet aircraft with a large capacity introduce mass travel. This is the Boeing 707, 1958. And of course, if we fast forward to today, we've got supersonic aircraft, and you can go from Melbourne to London in just a few hours. Well, unfortunately, we didn't go down that particular timeline. What we got instead was that. And I think we went astray there somewhere. Okay, all right, so never mind. In 1958, if you wanted to make a telephone call, you used a telephone. For the benefit of the young people in the audience, this is a device that has only a single app on it. It's the telephone app. You can't put the TokTik app on it for loading videos or anything, I think that's what it's called, on it. And you can't take it with you when you go because it's tethered to the wall by a cable. Today, of course, if you want to make a telephone call, you almost certainly have one of those, a mobile phone. In 1958, one of the first single-lens reflex cameras went on the market, the Minolta SR7. I have one of these in my vintage camera collection. And this device employs some of the best quantum nanotechnology you've probably never heard of, but unfortunately is now obsolete. But I don't have time to say very much about the wonders of electrons in quantum wells inside silver halide crystals. But it's a wonderful technology, now sadly obsolete. But fast forward to today, needless to say, if you're going to take a photo, you'll use one of these. In 1958, if you wanted to do a calculation, you used a slide rule, which exploited the properties of logarithms to convert multiplication into summation. And if you fast forward to today, you probably have a calculator app on one of those. Now let's take a big step back, 60,000 years ago. This is one of the first memory sticks that humans ever made with an early form of lithography. That is to say, the data was scratched onto the memory stick with a sharp rock, a lithography process. Unfortunately, what algorithm is used to interpret the 9 bits that have been stored carefully on this memory stick has now been lost, so we don't know the meaning of these 9 bits. But it's probably very important in human development. If we fast forward to 1958, Jack Kilby discovered a way of integrating transistors onto single chips of silicon. Before that, transistors came in individual packages and had to be soldered together. But this idea of integrating many transistors onto one chip eventually won him the Nobel Prize in the year 2000. It took the Nobel Committee a little while to figure out that this invention conferred the greatest benefit on humankind that should be. So, the Swedish committee ponders very slowly. And today, of course, if you want an updated memory stick, you don't have to scratch marks on bones. You can buy a 2 terabyte USB drive. That's an extraordinary amount of data that could be put onto one of these sticks. Now, what's interesting is that the technology to produce that sort of density of information is imperfect. And this memory stick has on board special error correction mechanisms to cope with the fact that not every memory element works all the time. And the onboard algorithms detect when memory elements begin to fail or didn't work in the first place and wall them off to prevent errors. So the key takeaway from this technology is that it's possible to build large-scale devices from tiny, tiny components with imperfect techniques and still have them work, just like the rover on Mars is imperfect because the radiation from space is constantly causing upsets in the memory, so you have onboard algorithms to detect and correct those errors. This is an important concept which I'll come back to later on. And today, of course, you can buy personal computer chips with billions of transistors integrated onto them, and the cost per transistor is about $10 nanodollars. That's an extraordinary number of human artifacts available at a very low price, or about 3 nano euros. A remarkable advance since 1958. So all of these bits and pieces go together to make what I call the first quantum revolution. The idea of quantum mechanics is the foundation on which all these gadgets, computer chips, optical fibres, mobile phones, supercomputers, solar cells, implantable devices, medical imaging systems, all of these things rest on the foundations of quantum mechanics. But most of these devices operate via classical principles. The fundamental quantum phenomena are buried down inside the chips, inside the silicon crystals, which comprise the fundamentals of these gadgets. And of course, this has led to a revolution in our society in the 20th century and the early 21st century, and here we see the modern way of having a conversation in a cafe using apps on the personal computers. I don't know if that's an advance or not. But this is the first quantum revolution. So now I want to move on and talk about the seeds of a second quantum revolution. And to do that, I want to illustrate some of the basic physics that have led to this that is leading to this second quantum revolution. And so it's a great thrill to be speaking to you today in Thomas Young's lecture theatre here at the Royal Institution, where he surely did this experiment to an interested audience such as yourselves back in 1802. Now, this experiment revealed that light was clearly a wave passing through space. In 1802, it wasn't clear what exactly was waving, but this was what Thomas Young did. Well, not exactly this, but close to this, and this is what it looks like in its modern form. First of all, you take a source of light. Of course, Thomas Young in 1802 didn't have an electric light bulb because it hadn't been invented yet, so he used the light from a nearby star, the sun, obviously. It passed it through a narrow collimator, whereupon it produced waves of light, which then it was incident on a barrier with two slits, and the waves that passed through those two slits then created an interference pattern on the screen. So I'd now like to demonstrate this in real time in the lecture theatre. So we've got we've updated it with using a laser, so it's a very bright source of light. Yeah, so let's... And in front of the laser, there's this beautifully handcrafted two slits. Is that right, Tom? Yep. And you can see the interference pattern created by the light waves passing through the two slits, where the peaks in one wave overlap with the peaks in the other wave, we get a bright line, and where the troughs of one wave overlap with the peaks of the other wave, we get a dark line, destructive interference. So this is very different to what you would get if light was classical particles. You could imagine throwing very small tennis balls at the barrier with the two slits, and all you'd get on the screen here is the shadow of the two slits, not this beautiful extended interference pattern that is a direct consequence of the wave-like nature of light. Thank you very much. And I should have mentioned that the diagram down here on the lower right is in Thomas Young's own hand, explaining why you get that row of that interference pattern of the bright and dark lines. Now, this, and here's one we prepared earlier in case it didn't work, but it did. Of course it did. It's physics. Always works. If we now fast forward just over 100 years to 1905, Einstein had his miraculous year where he published 4 new ideas in physics, the consequences of which we are still unpacking even in the 21st century. But the most radical idea that he published in 1905 seemed to contradict Young's conclusion from the two slit experiments that light was a wave. Einstein wrote in the introduction to one of his 1905 papers, according to the assumption to be contemplated here in his paper, when a light ray is spreading from a point, the energy is not distributed continuously over ever-increasing spaces, but consists of a finite number of energy quanta that are localised in points in space, move without dividing, and can be absorbed or generated only as a whole. And this sentence in Einstein's 1905 paper is widely attributed to be the most revolutionary sentence written by a physicist in the 20th century. So it's a tricky thing to demonstrate in the lecture theatre, but I want to give you an idea of how it works. First of all, I bought my woolen jumper all the way from Australia for this demonstration for you. And those of you who were admiring the painting out the front of this lecture theatre will recognise this bit of apparatus that appears in the painting. It's an electroscope. And what I'm going to do is I'm going to charge up the electroscope by rubbing a few electrons off this plastic rod and bringing it into the electroscope, grounding it and then moving it away. I've just charged the electroscope by induction. For those of you who are sitting up the back, it might be a bit hard to see, but oh, there we go. So we can see the 2 leaves of this electroscope have been deflected because they've been charged up. Now, this electroscope has got a sheet of zinc on the top of it, and I'm now going to shine a very bright light onto the zinc and knock electrons out of the surface of the zinc with this beautiful incandescent torch that's come out of the archives of the Royal Institution for me to use in this demonstration for you tonight. Is anything happening? Nothing's happening. Of course nothing's happening because the photons in this torch are too feeble individually to knock an electron out of the surface of this zinc. Now, the zinc plate. Now, we tried every other bright light in the possession of the Royal Institution this afternoon, including their very dangerous ultraviolet light, but unfortunately their ultraviolet light is not dangerous enough and the photons are just not energetic enough. So to show you this demonstration, I'll have to show you a demonstration recorded in my laboratory in Melbourne. But if you use photons that are individually sufficiently energetic to knock electrons out of the surface of the zinc, you discharge the electroscope. But this was Einstein's idea from 1905 to explain that phenomenon. The light coming out of that torch or out of that laser or out of the very dangerous ultraviolet lamp that I'll show you in a moment consists of individual packets of energy that cannot be further subdivided. So in other words, you can't have half a photon. You've got to take the whole photon or not at all. So this was a rather unusual idea in 1905, but it's been tested over and over again and found to be true. And this is the photoelectric effect that Einstein eventually got the Nobel Prize for. So here's the basic idea. There's your piece of zinc, which has got a whole lot of electrons embedded in the surface. Here's some waves of light approaching the surface of the zinc. And here is the photon associated with those waves. Now, here's where the strange idea comes in. Although that wave spreads itself out across the entire surface of that piece of zinc, the photon can only be absorbed in its entirety or not at all. So it's like the photon, each photon, somehow tastes all the electrons on the surface of the zinc because it's a wave as it approaches it, and finds one electron that it likes the taste of. I'm being metaphorical here. Photons don't taste. And it knocks one electron out of the surface. So it's as if the photon, in its wave-like manifestation, is dispersed over a large area. It's in multiple places at the same time, but is all absorbed finally in one place and gives all its energy to one photon. So this is what we can do in Melbourne with our very powerful light. So I'm just going to fast forward this to 2 minutes. We don't need the sound on this because I'll do the voiceover. So here my trusty assistant Steve has got this very dangerous ultraviolet light. He's going to turn it on. Don't look at it, Steve. No. Then he brings it over the electroscope, shines it on the zinc plate, and you could see the leaf of the electroscope deflect as the charge leaks away into the air in the room. So that's what happens if your photons are sufficiently energetic to interact with the electrons and dislodge them one by one, and none of these other lights had energetic enough photons. Another way of looking at this, which is easier perhaps to understand, is imagine you're surfing. I guess this doesn't work so well in the UK as it does in Australia. But imagine you're surfing and you see this wave approaching and there's a whole bunch of surfers lined up ready to catch the wave. In Einstein's idea, only one surfer can catch the wave. So it's like the other two surfers, left and right, are left flat in the water, and just the surfer guy in the middle catches the entire wave. And so in some ways, the wave, the function that describes the wave, collapses just to one point when it has to interact. This is a fundamental mystery of quantum mechanics. The other day, under the terms of the fellowship, I have to go around giving lectures at different universities, and I went down to the University of Surrey, caught the train down on one of the non-strike days, I emphasise, and I saw this sign at Guildford Station, and as a physicist this makes me very nervous because they're asking me to spread out along the platform like a quantum particle, but I'm too big, I'm a classical particle, so I couldn't obey that sign. Or maybe just reading the sign caused me to decohere into this one place so I could read the sign. I don't know. I think it's a very disturbing sign, and there should be an asterisk, do not take literally. Let's fast forward to 1911, when Ernest Rutherford reverse engineered the atomic nucleus, discovered the nucleus surrounded by its cloud of electrons. The nucleus is like the size of a dust particle floating inside a cathedral representing the cloud of electrons, something very tiny and very dense. And then his postdoc, Niels Bohr, just a few years later, discovered the quantum atom. He discovered how the electrons that orbit that nucleus that his supervisor had discovered, how they orbit. And they orbit not by classical trajectories like you have with planets orbiting the sun, but they orbit in quantum mechanical standing waves. Now, what's remarkable about that idea is that quantum mechanics is starting to be manifest in more and more places, not just with Einstein's photoelectric effect. The other remarkable thing about Bohr's paper, both Rutherford and Bohr were working at the University of Manchester at the time of these two discoveries, where I'm based at the moment, was that Bohr's paper was read for the first time at a conference in my physics department at the University of Melbourne. I wasn't there in 1914 when it was read. But the British Association for the Advancement of Science had its meeting in Australia in 1914. It rotated around the Commonwealth. Mostly it was within the UK, but once it went to Canada, and this time it went to Australia. Rutherford was the president of the British Association. His postdoc, Niels Bohr, wasn't there. He was on holidays, so Rutherford read the paper. And it's remarkable that this original idea of the quantum atom should have been heard at a conference for the first time in the old physics building at the University of Melbourne. We have detailed records of the meeting, and the chemists in the audience thought that physicists should stick to physics and not meddle in atomic theory because everyone knew atoms were square. But they reluctantly conceded that there seemed to be some grain of truth in these ideas, even though they were quite radical. But we now know that we can describe the quantum mechanical nature of matter using Schrödinger's equation. Now, just in case someone stops you on the tube on the way home and asks you, did you go to that Einstein lecture at the Royal Institution and did you see Schrödinger's equation? You can say, yes, we did. But Schrödinger's equation, there's nothing mysterious about it. It's simply what we're already familiar in the classical world, that the energy of a particle, such as this cricket ball propagating through space or this moon orbiting that planet, is just given by the sum of the energy due to motion, the kinetic energy, plus the energy due to any interactions between the two objects, such as gravity or electrostatic forces. But for quantum mechanics, we need to be able to describe things that are in many places at the same time, a wave. And so we just translate these classical ideas, the kinetic energy and the potential energy, into functions so that we can find the shape of the wave, represented here by the Greek letter psi. But it's exactly the same concept. We're just replacing scalar quantities with function quantities. And that then, even for a simple system like an electron orbiting a proton in the hydrogen atom, leads to these beautiful three-dimensional shapes that describe the nature of the electron, quantum mechanically speaking, in its orbit around its proton nucleus in the hydrogen atom. And this can be applied to many other elements in the periodic table, including phosphorus atoms in the silicon crystal, which I'll come to later on. So, the next step in our quantum mechanical journey is the discovery of spin. Now, it's worth spending just a few moments to talk about spin because it's actually a rather strange concept. First of all, I have a child's toy here, a very nice top. It's got a sharp point here, which means you just can't balance it, you know? Just won't balance. But look what happens if you give it a bit of spin. It does balance. It doesn't fall over like it does what would happen if it wasn't spinning. But you can see in the gravitational field of the Earth, gravity is trying to tip that over. And for reasons to do with the velocity vector constantly going around in circles of the rim of the top, it precesses around the gravitational field direction, which is vertical. And as it slows down, due to friction with the table, that precession or that wobble becomes more and more extreme. But this is, until finally it succumbs to gravity, as it always will. But this is a classical object. It turns out, down inside the atom, the electrons that are orbiting the nucleus also have spin like this, and so we represent them by objects that look like this. So, and this is just one I made myself from the stuff I got from the local craft shop and a very nice tube of self-adhesive glitter. So you can think of this as an electron or an atomic nucleus, and it's spinning about its axis, and we represent the direction of the spin using the right-hand rule, where my thumb points in the direction of the vector representing the direction of the spin. Now, what was discovered in 1921 was that in a silver atom, which was known to have no spin except for the last electron added to make up the whole atom, which was all by itself in the outer shell. So the whole spin of the silver atom was basically carried by that last electron. And when you boil silver atoms in a vacuum out of a furnace and pass them through a very strong magnetic field, you find that the beam of silver atoms splits in two when it passes through the magnetic field. In the same way we saw the wobbles of this top due to the presence of the gravitational field. But now we're talking about a quantum mechanical spin in a magnetic field, but the physical principles are very similar. And when this experiment was done, first of all, this is the result of a beam of silicon atoms hitting this postcard. Without the magnetic field, you just see a line of silver atoms piling into the card. Then when you turn on the magnetic field, you find the line splits in two. They're not two parallel lines because you need to use a very strong inhomogeneous field. But this discovery was immediately reported to Niels Bohr, who by then had left Manchester and gone back to Copenhagen to head up a new research institute, because it was so exciting, so unexpected, that down inside the atom there were objects we now know are the electrons that were spinning, and they precess in a magnetic field in the same way this top precesses in a gravitational field. And what was mysterious was that the spin could only have two possible orientations, reflected by the fact that there are only two lines here. So it was concluded that the quantum mechanical attribute of an electron was such that it could either be spin up or spin down, but nothing in between. Space was found to be quantized. It was like this top could only wobble like that or like that. Nothing in between, which of course is not the case for the real top because it's a huge macroscopic object and quantum mechanics is hidden. So this was a further quantum attribute of matter that was discovered in 1922. Now, you can see the same effect by taking light from the sun and passing it through a slit and into a spectrometer, like dispersing the light through all the colours of the rainbow. And here is this black line represents the slit of a spectrometer, and it passes across a sunspot where the magnetic field is very strong. And sure enough, when you look at the colours of the light coming from the surface of the sun, you find that away from the sunspot it's a single colour, and then as the light comes from the sunspot, in this case it splits into three, not two, three. And this was later found to be due to the fact that the spin had a different quantum number, an integer rather than for an electron, the spin is always 1/2. So this uncovered a lot about the internal machinery of how electrons orbited the atomic nucleus. So all of this stuff was boiled down into the first iteration of quantum mechanics, of which Paul Dirac here in the UK was one of the leading exponents. But in 1928 he made the somewhat depressing observation: the underlying physical laws necessary for the mathematical theory, Schrödinger's equation, of a large part of physics and the whole of chemistry are thus completely known. I don't know if the chemists would have agreed, but that's the physicist's view. And the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. So let's go back to the caffeine molecule. What a wonderful molecule. It docks with all the physics receptors in the brain and makes them go round faster, and you get new ideas, and it's great to talk about quantum mechanics and spin and Dirac's depressing observation. But the caffeine molecule has got 100 spinning electrons orbiting the carbon, the hydrogen and the oxygen that make up the molecule. That's a little electron I made as well, which can only have two orientations in space. And the number of electron-electron interactions across those 100 outer shell electrons in the molecule are governed by Schrödinger's equation, but there are so many interactions that even the world's best supercomputer is powerless to calculate the structure of the caffeine molecule. It's just too complicated for a classical computer to solve. Even the most powerful supercomputers today can only do about 30 electrons, and every time you add another electron, you get more and more electron-electron interactions, and the problem becomes exponentially difficult. So there it sat for 70 or 80 years. But in 1959, Feynman gave this remarkable lecture, There's Plenty of Room at the Bottom, where he put forward this idea for a new type of calculation, not just using classical circuits, but a system involving the quantized energy level or the interaction of quantized spins. In other words, to build a computer that employs quantum spins as its bits instead of classical bits that would allow you to use a quantum system to model another quantum system. But there was no technology in 1959 to do anything with that idea. But we are trying to do something with that idea, and this is a phosphorus atom that goes into a silicon crystal beautifully. And we can see it's got a nucleus spin inside the phosphorus nucleus, and there's a single electron orbiting around it, which also has a spin, which can be harnessed for technological applications. So let me explain the power of a quantum bit instead of a classical bit. First of all, let's take this abacus, used for thousands of years, and the same principles behind that abacus is also at the heart of the classical processing that's going on in my mobile phone here. Now, the way an abacus works, for those of you who need a quick refresher, is that the value of the bit is determined by its position on the wire in the frame of the abacus. So that bit on the top right there is in the down position, that's called 0. But if you flip the bit and put it to the up position, that represents a 1. So effectively what you've done is you've replaced the bit with an arrow, which we can call a vector, and by flipping the vector through 180 degrees, you change the value of the classical bit. But they're the only two possible values that classical bit can have. It's either down, 0, or up, 1. Now imagine grabbing the wire out of the frame of the abacus and allowing it to occupy any orientation in space. This is what a quantum bit is. A quantum bit exists as a superposition of being in two places at the same time, like Einstein's photon being a wave, and it can be in the sum of the 0 state and the 1 state, which determines its orientation in space. There's only one catch. You can exploit this remarkable large versatility, providing you don't observe the qubit. Because as soon as you observe it, it'll instantly decohere, just like the photon changes from a wave to a particle when it interacts with just one electron, into its classical values of 0 or 1. So you can do massive computations to exploit this enormous phase space, as we say in technical speak, providing the quantum computer exploiting this technology doesn't interact with the outside world until it finishes the calculation. That's a challenging thing to do. Nevertheless, in 1998, a young postdoc at the University of New South Wales, Bruce Kane, published this single-author paper in Nature, the journal, a silicon-based nucleus spin quantum computer based on phosphorus atoms embedded in a silicon crystal lattice. This paper has been cited thousands of times and triggered a reappraisal of the idea of qubits in an engineered device. Today, with my colleagues in the Centre for Quantum Computation and Communication Technology in Australia, we have refined Bruce Kane's architecture into something we believe we can build based on single phosphorus atoms embedded in silicon, each of which is individually controlled by electrodes integrated into the surface of the chip in the same way there are myriads of electrodes integrated into the classical devices inside this phone. So basically, we're using the standard tools of the semiconductor industry, perfected now over 60 or 70 years, to enter the quantum domain. So this is now the second quantum revolution, just emerging. And why do we want to do this? Well, getting back to Feynman's idea of using a quantum system to model another quantum system, one day the next pandemic may be fought not with test tubes and Petri dishes in the traditional way, but by reverse engineering the spike protein in the next virus, and then engineering in silicon the shape of a molecule needed to gum up the works and act as a vaccine. This is a dream which would have enormous benefit. And today, quantum computers are already being built with tens or even hundreds of qubits, where the first tentative steps in that direction are being taken. But if you were going to devise a vaccine, you're going to have to do massive calculations. You will need millions or even billions of qubits. And what's the cheapest qubit it's possible to make? A qubit based on a single atom. Atoms are really cheap. There are other quantum attributes, including entanglement, barrier tunneling, coherence, decoherence, Schrödinger's cat, and teleportation that could also be incorporated into new quantum technologies, but I don't have enough time to say very much about them. So in the last part of my talk, I want to describe some of the work we're doing in building a large-scale device by using ion implantation to insert single phosphorus atom qubits into silicon crystals. And this cartoon shows the way it might work. We see a whole array of phosphorus atoms just below the surface of a silicon crystal, and each atom is controlled by an electrode integrated on the surface, and by changing the bias voltages on the electrodes, we can cause the qubits to interact without doing any measurement so that they retain their delicate quantum states of being in two places at the same time. So this brings me to the classical quantum divide. After Young's two-slit interference experiment, the question was asked, okay, it works beautifully with photons, does it work with matter? Can a particle of matter, like an electron, be in two places at the same time? And this is a diagram taken from Feynman's famous lectures in physics. I'm putting this up because I once sat next to Feynman at a colloquium when I was a postdoc at Caltech, and I tell you, the charisma, wow, it was amazing. What a remarkable guy. Not a little dangerous, perhaps, but a brilliant physicist. But in his famous textbook, he described the way matter behaves using Young's two-slit interference experiment. He said you can take an electron gun emitting particles of matter, electrons. You can direct them to a wall that contains two slits, and over here on the backstop there's a detector for measuring the position of all the electrons that pass from the electron gun through the barrier to the detector. And when you do this, he said, you will end up with a Young's two-slit interference pattern, not the classical shadow of these two slits. But he comments, this experiment has never been done in this way, because when these lectures were published in the early 60s, there was no technology for detecting single electrons at a time. But folks, let's look at the shocking truth of the way this experiment works. An electron, a particle of matter, emerges from the electron gun and passes through both slits. The electron, a particle of matter, is in two places at the same time, because somehow it turns from a particle when it emerges from the electron gun into a wave, passes through both slits, and then converts itself back into a particle to make the detector go ping, and it all goes to one place, just like Einstein's photon in the photoelectric effect. Humanity finds this rather shocking, the idea that a particle can be in two places at the same time. So when we teach this in undergraduate physics, we bury it under a thick layer of mathematics to conceal from the students the shocking truth of what's actually happening here. And if they ask questions about what's actually happening here, we just say, shut up and calculate. I've been doing it for 20 years. But I reveal the shocking truth. So here we have the electron behaving like a quantum wave as it passes through both slits at the same time. And then here we have the electron behaving like a particle when it all converges on the detector and makes the detector go ping. So when you move the detector up and down along the backstop, you record the intensity of the electrons forming the interference pattern, which you saw in the lecture theatre at the beginning. And so today, this is the quantum classical divide. We need a classical readout device for our quantum mechanical operations that we've engineered into our device. And I was very taken with this paper published in 2013, where the authors are very cheeky. They copy Feynman's diagram from his book and say, actually, we have done that experiment. They did take an electron gun. They did pass the electrons through the two slits, and they did have a detector, and they recorded the interference pattern as the electrons interfere because of their quantum attributes. Furthermore, a group in Austria has done the same experiment with a buckyball. 60 carbon atoms in this giant molecule fired at a grating, and the molecule can be in 2 or 3 places at the same time and make a Young's two-slit interference pattern. I find that very spooky, but a wonderful aspect of the real world. And today, this classical quantum divide, seen here where we have quantum attributes, is engineered into quantum computer devices, the prototypes. These are superconducting qubits consisting of little magnetic circuits where the magnetic field can be up or down, or in a superposition of up and down, and each of these devices now has a classical readout device to report the results to the outside world. Our architecture consists of a single phosphorus atom in a block of silicon with control circuitry. The spin of the phosphorus atom is our quantum particle. It can be spinning in both orientations at the same time, represented by the double arrow here. And then there's a single electron transistor formed by these electrodes, which is connected to an oscilloscope. And all these guys are looking at the oscilloscope to decohere the nucleus into either the spin up or the spin down orientation. The observer has to be in the loop, it seems. And the first time we got this to work, I was in my office in Melbourne. I got the call from Sydney where the measurement is done after we implanted the phosphorus atoms, and they said it's working. After all these years of work, finally we've got a device that is displaying the quantum attributes we've been eagerly seeking. So I said, don't touch anything, I'm coming right now. I went to the airport, I got on the next available flight. You know how much Qantas charges if you go to the airport and say, put me on the next flight to Sydney? It was extortionate, but I was in the lab a couple of hours later and I saw with my own eyes something I'd been teaching for 2 decades actually happening in the laboratory. We could see the electron spin orientation, we could see the nucleus spin orientation, we could see that nature was digital at the fundamental level. So this is the heart of our device, a silicon crystal lattice consisting of silicon atoms, and one of which we replace with a phosphorus atom using ion implantation. Now, silicon is not perfect. There is a rare isotope naturally occurring called silicon-29, about 5% of natural silicon, and it has a nucleus which is a bit peculiar. It's got an extra neutron, and that extra neutron confers spin on the nucleus, whereas all the other silicon isotopes have no spin in the nucleus because all the nucleons are beautifully paired up together. So that's like having a little bar magnet inside our chip, which is interacting with our phosphorus atoms and destroying the quantum coherence. So step one is to remove the silicon-29s and replace them with silicon-28, the zero-spin isotope. And this is like a vacuum with nothing going on except what we've engineered into it with our phosphorus atom. It's the next best thing to a real vacuum for doing quantum mechanics. We then use radio frequency pulses to flip the spin orientations from the 0 state to the 1 state, or indeed to put them in the quantum superposition of being spin up and spin down at the same time. This is what the device looks like. This is about, I guess, about a million times actual size on the screen in the lecture theatre. Right in the middle is a small area where we implant a number of phosphorus atoms, and then we use these control gates to tune in on just one of them, and that's where we do our quantum experiments. And this is what it looks like in a cartoon. A single electron is brought across onto the phosphorus atom. Then we do a radio frequency pulse to put it in the quantum superposition. This is all at 100 millikelvin. It has to be very cold. And then by controlling the position of the electron, we move it back into this single electron transistor. There's a flow of current, and that's connected to an oscilloscope, and we can see the quantum state of our electron, and then we reinitialize the device, and it starts all over again. So here's the spooky quantum bit in our device. Einstein, in 1916, said, imagine you've got a quantum object which can be in two energy states, a low energy state and a high energy state. And that is indeed what happens when you put a spin in a magnetic field. It's like putting two bar magnets together. When the north and south poles are together, they stick together beautifully. But if you try and push two north poles together, it doesn't work. It's in a higher energy state and will spontaneously flip. Now, in a spin, which can be up, the low energy state, or down, the high energy state, you can flip the spin by hitting it with a photon. There's a lot of photons going on here, but this is a microwave photon. Now, Einstein said, if you're in the high energy state after the low energy state absorbs a photon and goes to the high energy state, another photon of the same energy will cause it to decay back to the ground state. So while the photons are on, they are both lifting the spin into the high energy state and inducing it to decay back into the ground state. So when you turn the photons off, the spin is in this quantum superposition of being up plus down. And because I've been lecturing to undergraduates, I have to put, this is the spooky quantum bit of the device. So, sorry about that. And then when you read it out, you decohere it. The detector goes ping, either in the spin down state, high energy, or spin up state, low energy. And you repeat that over and over again with increasing time intervals after you turn the photons off. And if this was a classical particle, 50% of the time when you do the measurements, you'd find it's in the high energy state, and 50% of the time it would be in the low energy state. It would just be random. And indeed, Galileo and Newton would predict this is the result you would get for this experiment. But when we do the experiment, because this spin is a quantum entity, we find it's not a probability of 50% up and 50% down. It actually oscillates between the up and down configurations because of its quantum nature, the wave-like nature of the spin. And the longer those oscillations go on, the more quantum calculations you can do when it's in that superposition of quantum states. And we found that the atomic nucleus can last for more than 30 seconds in this superposition of up and down because of the duration of these oscillations. And 30 seconds is an eternity for a quantum state. And so we were very pleased to get this expected quantum state. So this is our device. We remove the silicon-29s, we implant a few phosphorus atoms, we tune in on just one, and we do all these experiments. But this is not good enough for a large-scale device. So just to conclude, let me explain how we're going to take the results we've obtained just on our single phosphorus atoms and take it to the tens or even hundreds. This is a silicon lattice. We implant phosphorus atoms into it using the standard techniques of the semiconductor industry. There's probably 15 or 20 different ion implantation steps that have gone to make the silicon chip in here. Then we heat up the crystal and we push the implanted phosphorus atoms onto the crystal lattice site. But the way that's done in industry, it's like raindrops on a window. The raindrops fall at random points on the window. This is not good enough for making a large-scale device. We have to have order. And so what we want to do is make this deterministic, non-stochastic. We want to put the atoms in an orderly array so they can be coupled to the surface control electrodes, and we can do large-scale quantum computations. And it better not take too long. So we have re-engineered an atomic force microscope that has the precision to localise the implants using this tiny nano aperture. So the ion beam rains down on the cantilever, there's the little tip of the atomic force microscope, and every time a single phosphorus atom passes through the nano aperture and implants, we hear a click. And so here, folks, is the sound of single phosphorus atoms being implanted into a silicon chip. Let me just get the sound going here. Bit uncertain, that one. Oh, another one. You can hear, it's like rain on a tin roof. And every time we hear one of those pings, we move the cantilever to a new location and wait for another one to come down. This soundtrack was featured on the Australian Broadcasting Commission's Sounds of Science. So if you Google it up, you could download it and use it as your ringtone if you wish. So we are now in the process of building a large-scale device using this technology. We have already built a 3-qubit device. Just by luck, we found 2 phosphorus atoms which were close enough together that we could couple them. And this is the artist's impression of those 2 phosphorus atoms with a single electron in orbit around both of them. This is an artist's impression, but you've got to have fancy artist's impression if you want to get on the cover of Nature, as we did back in January with this discovery. And this device worked beautifully. We were able to maintain the spooky quantum state for a very long time, and we made a very high fidelity gate set, something that is the building block of a large-scale machine. And this was very satisfying, even though we made it only one device out of many we made work like this, because we were just implanting the atoms at random. But now we're going to impose order on our device and build large-scale devices of single phosphorus atoms in our ultra-pure silicon. And so I hope you'll stay tuned for more developments in this area in the years to come. Thank you very much for your attention.